I'll give it another 30 seconds or so. I'll use this time actually to just talk about an initiative we're running around these new speakers. If anybody might have seen me talking about this already, but if anybody is interested in stepping up onto the conference circuit, being the next Simon Ritter, then feel free to let me know. We're doing quite a bit of work in this space now. So we're running fortnightly lightning talks events. Can see John McMullen now just turned his camera on. He spoke at our last one. So yeah, we've run 4 of these events now, so everyone's welcome to sign up and get involved. Okay, we have a bunch more people joining, including Dennis. Hopefully this will
you'll get in. Yeah.
Okay, right. I'm going to share my screen briefly. Then I'm going to just say a few words to introduce myself and the LJC, and then I will hand over to Dennis and Simon.
Okay.
Right. Can everyone see my screen there? Some people. Okay, cool. Okay, so yeah, I'll just say a few words, as I say, a bit of background about the LJC for those of you who this is your first event or your first in a while, or tuning in later. So the LJC, the London Java community, or the London Java user group, we're a very well established, highly active group. So you can see some numbers there, 7,500 members now. We've organized over 600 events, and we are 13 years old this November. But what a lot of people don't necessarily know about the LJC is it's more who we are behind those numbers. And that really is these values that we try to embrace around what the power of community can be, and how much more you can achieve as a community than as individuals. So for me, that's all around the mentoring, the learning, and teaching. So that's always been my passion within this side of things, bringing people together to educate others and help other people learn. And for others in the group, this is more on the tech side of things. So all things like adopt to JSR, adopt OpenJDK. These were all things that came out of the LJC from people getting together, clubbing together, and really doing more with collaboration. So as for who I am, my name is Barry Cranford. I'm the founder of the LJC. I'm not a developer myself. I'm in fact a recruiter. I run a recruitment company called RecWorks, which many of you will know. So at RecWorks, whilst we do recruitment to make money, we believe that recruitment can be a force for good in the industry beyond just getting people jobs. Again, specifically, this is around this mentoring and learning piece. So a lot of the work that we do sits somewhere between giving back to people that we've worked with and paying forward to people that we hope to work with at one point in the future. So examples of this include the 600 events that we've organized within the LJC. We've run 2,000 mentor introductions, personal introductions now within the Meet to Mentor community, and the new aspiring speakers group that we're running, which is all around trying to help people get a leg up, get onto the conference speaking circuit and learn from other people within that. If you're interested in any of that, speak to me afterwards, LinkedIn or Twitter at BC RecWorks. Again, it's all powered by recruitment. So the only money that we make is coming from people, from us getting people jobs. So if you're looking to hire or you're looking for a job yourself, then you're always welcome to come and find me. Anyway, with that, I will get out of their way now, hand you over to Simon and Dennis, who are going to be speaking on architecting low latency Java systems at massive scale. So Simon, I'll hand over to you now.
Yeah, let me just share my screen. And then we go to slideshow.
Hey guys, while we are starting, could you confirm you can hear me well?
Oh, good. Dennis is here.
Yeah, we can, Dennis.
Yeah, unfortunately, I had troubles with Zoom in the last moment. But finally, restart of the laptop and an upgrade helped me out.
Just in the nick of time.
Yes. Okay, I'll let you get started, Dennis, because the first bit's like your books and stuff, isn't it? So.
Yeah, guys, just in case today we are going to refill out a couple of low-level engineering books. So I do believe that we are going to paste this link to the questionnaire in the chat window. And also you will see the same slide in the end of our presentation, just in case you'd like to know that that's something you expect to get today. All right, Simon, let's move forward with the most pleasant.
Okay, there we go. Yes. Yeah. So I'll just introduce myself, and then you can introduce yourself and carry on. Yeah, so my name is Simon Ritter. I am the Deputy CTO at Azul Systems. I have some history in terms of Java. I joined Sun Microsystems in 1996, just about a week from when JDK 1.0 was launched, and spent 14 years at Sun, followed by 5 years at Oracle after they bought Sun. And I've been at Azul for the last 4.5 years. So I've pretty much followed Java over most of its history. And so I'll be talking about how we do low latency in terms of the JVM. Dennis?
Yep, talking about myself, my name is Dennis Nagda. Thanks everybody for being on this line. Presently, I'm taking the role of Vice President of Developer Relations at GridGain. Throughout the conversation, you will understand what GridGain does, but also I'm an Apache Ignite PMC member and committer. I'm working closely with the Apache Software Foundation. And before joining that foundation and before joining GridGain, I used to work for Sun Microsystems as well, belong to that Sun family, but I was mostly on the Java Micro Edition and Embedded Edition ends. And also I spent quite a lot of time working at Oracle after that company acquired Sun. So having said that, I also have a pretty large experience in Java. And right now I will be showing you together with Simon how you can take Java and make it scalable and really fast.
Okay, so what we start with is a sort of an example of how latency can be a really, or avoiding latency can be a really useful thing. And we found this really good example, which is Southwest Airlines. Now, if you go way back into 1972, Southwest Airlines was a very new company, and they had all of 4 airplanes. And in order for them to continue doing business, they ran into some sort of financial issues. In order for them to continue doing business, they actually had to sell one of their 4 airplanes. So they went from having 4 airplanes to having 3 airplanes. Now, typically, you would just expect everybody to go, okay, only got 3 airplanes. We're going to have to cut a number of routes and therefore reduce the number of flights we can do, and that's going to affect our revenue. But what they did was they took a different approach. They said, okay, how can we reduce the latency of the turnaround of the aircraft? And by doing lots of different things and getting everybody to work together very carefully, they managed to reduce the turnaround time of an aircraft to 10 minutes. And that meant that they could do the same number of flights, the same number of routes with only 3 aircraft rather than 4 aircraft, which is quite impressive, really, when you think about it. And so it was this idea that by reducing the latency, they were able to increase the throughput, increase the load on the system without sacrificing any of the service that they were giving to their customers. So really, it's this whole idea of how we can reduce latency and provide a better service for our customers. So, Dennis.
Yep, and right now, if you're jumping back to our domain, to the world of software systems, here's, guys, we wanted to walk you through some of the most notable examples of low latency systems. Usually low latency systems, depending on your low latency system, you might fall into various ranges of how that latency is defined. The very first and obvious example, everybody makes purchases offline or online. And whenever you swipe a credit card, the backend systems and databases of banks as well as credit card companies, they need to process that payment. They do various fraud detection checks, verifications, and also they need to eventually either reject or accept your payment. And they have only a fraction of from 20 to up to 200 milliseconds, based on my experience, to process those operations. That's how less time they have to kind of either accept or reject your payment. If we move forward and check how low latency requirements are applied in the telco sector, let's take 5G based solutions as an example. So with those, most of the applications and most of the services that will be powered by 5G infrastructure have to complete their operations within the boundary of 1 millisecond up to 5 milliseconds, like for most of the operations, whether you are processing traffic or whether you are doing some management operations. And finally, the most extreme use case is electronic trading. You might be a trader who is at New York Stock Exchange, or who is on the New York Stock Exchange floor, or you might be using some, common tools that monitor market ticks. And backend systems of the electronic trading platforms have to operate within boundaries of microseconds. And these are the examples of the low latency systems that software engineers have to deal with. But Simon, let's see whether Java is good enough for those cases.
Yes, so obviously one of the things that is an issue is garbage collection, because the real issue with garbage collection is simply that we can't predict when it's actually going to happen. So if we can avoid that problem, then obviously we can solve many of the issues around latency. So let's have a little talk about that. So the first thing is, in terms of requirements for low latency, we need predictable and consistent latencies. And in order to do that, we have to essentially eliminate the problem of garbage collection. Now, I'll talk a little bit more about this as I get into the Zing part of this. But as I say, the fact that garbage collection is non-deterministic and we don't know when it's going to happen, it's not a regular thing, it only happens when it needs to happen. And because the algorithms that most people use for garbage collection involve pausing application threads to do the work of garbage collection, that introduces pauses, which can be very variable in terms of the time that we get involved in those particular pauses. So,
when it comes to the latencies and high and throughput, so here is we want, if you're already designing a Java-based software system for those applications, why don't we use main memory as our primary storage? As I will show you folks throughout this presentation, it's obvious that we can read and get records from RAM is much faster than from disk. And the benchmarks and the tests that we run will only confirm that there is a true benefit of having all the data in memory. Because eventually that's how you can get the lowest latency possible with the high throughput that is needed for your applications. And the final requirement that comes to the scalability. Most of the systems that we design today might not be able to tolerate the workload of tomorrow. Thus, it will be ideal if this Java-based solution if that Java-based solution is able to scale out, if it can go ahead and scale horizontally. And here is we are talking not only about our services and applications, but also we are talking about the backend. We are talking about the databases. So finally, how what exactly Simon and I will be focusing on today? How that Java-based solution that we explored and want to share with you looks like. First of all, that will be a distributed system that is powered by Apache Ignite. Apache Ignite, in short, is an in-memory computing platform that is designed to store your data in a scalable way, in memory by default, and then it supports a variety of APIs we can use to access the data. But also it's worth mentioning that every Ignite individual cluster node is no more than a Java application. And to be able and if you want every Ignite cluster node to perform the fastest way possible with the lowest latencies, we checked and used Azul Zing as our target Java virtual machine. And applications, our applications would be classic standard Java applications connected to the cluster. And also those applications would be using Ignite APIs to process different data, to issue transactions, and to be able to do this with consistent latency and decent throughput, we will also be running on Azul Zing. All right, so why don't we go ahead and check Azul in detail?
Okay, right. So what I'm going to do is I'm going to explain to you what we do in terms of the JVM. And the first thing that we need to look at is the idea of what do we actually mean by speed in terms of the Java world, because this is quite important, is understanding the impact that many different aspects of the JVM have on what we do in our applications. And to kind of illustrate this, what I did was I thought to myself, okay, let's put together what we would expect to be the ideal performance graph in terms of the JVM to run our application. And this is what I came up with. Now, it's a pretty unexciting graph. It's pretty straightforward. And all we're really seeing here is the idea that for an ideal system, what we would like is for the JVM to start up and give us the maximum level of possible performance it can right at the very beginning. So we're 100% level of performance right at the beginning, and we simply give all of that for the entire time that the application runs. Now, it's very obvious that that's what we want. The reality, though, is somewhat different. And so what we tend to see is a graph that looks a lot more like this. And it's worth just spending a few moments explaining why we see a graph like this in terms of the JVM. So the first thing is that when we start our application up, what we've got is bytecodes. So we have class files, we have jar files, and the JVM needs to load those class files in order to execute the methods within our classes. Bytecodes, as we know, are instructions for a virtual machine. Java virtual machine, clues in the name. And in order for those instructions to be executed on the actual platform that we're running on, they need to be converted or interpreted from bytecodes into native instructions or operating system calls. Now, the problem with that is it's a slow process in terms of interpreting those bytecodes. And there's nothing very clever going on in the sense that we don't cache anything, we don't do anything in terms of optimization. Every time we see a bytecode, we do the same thing in terms of interpreting it and converting it. So we start off rather slow, and that's the way that Java started out. Everybody kind of criticized Java initially for being a slow language compared to C and C++. So the developers of Java looked around and said, how can we improve this? And they said, okay, well, there's this other technique, which is called just-in-time compilation, JIT. So what we do now is we run our application and we monitor how many times methods are called. We count that so that when a particular method reaches a certain threshold and it becomes a hotspot in terms of the code, hence the name of the JVM, what we do is we say, right, rather than interpreting the bytecodes of that method every time, let's compile it into native instructions and just run those native instructions. So it will run faster. To do that, we use initially the C1 JIT compiler. And the C1 JIT compiler is designed to compile code very, very quickly, but it doesn't optimize our code. It just compiles it using basic compiler techniques, but doesn't apply a lot of optimizations. So then we continue to run our code using this C1 compiled code, and that also collects profiling information, telling us how the application is actually being used, what methods are doing, all those sorts of information. And then at another threshold, once the method has been called a certain number of times, we recompile it. And we use the C2 JIT compiler. In this case, C2 is designed to do a lot more optimization. So we get much better performing code. But what we see as the application gradually compiles more and more of these methods is we get these dips in performance, and those are due to de-optimizations. Now, de-optimizations occur because one of the things that we can do in a JIT compiler is speculative optimizations. We look at the way the code has executed so far, and we predict that in certain circumstances, it will continue to do exactly what it's done before. And we can optimize things like if statements or the way that methods are called and things like that based on that history. But sometimes our assumptions are wrong, and so we have to then throw away that code and recompile it based on the new information that we have. So we get de-optimizations. Then at some point, we're going to reach our steady state where we've compiled all of the hot methods, we've used C2, we've avoided all the de-optimizations, and we have our optimum level of compiled code. But then we still see these dips in performance, which affects latency. And those are due to garbage collection. And we're all familiar with the idea that the garbage collector kicks in, needs to do some work, pauses the application threads, and that introduces latency to our application. So in terms of the challenges that we're dealing with in terms of the JVM, we've already kind of stated this, but it's a managed runtime environment. That's really good for us as developers because lots of things that we would normally have to concern ourselves with, we let the JVM take care of. But there's two big things. One is obviously the garbage collector, the fact that it is inherently non-deterministic. And for the majority of algorithms, the pause times can be big. Now, if you're running in a sort of a trading environment on a sort of fintech system, then tens of milliseconds could be a big pause time. If you're not so concerned about that, maybe you're going to see a few seconds of pause time. The worst pause time I ever heard of with garbage collection running on Java was 1.5 days. Now that's a pretty extreme garbage collection pause, really extreme garbage collection pause, but you don't normally see them as big as that. The second thing, as I've already said, is bytecodes, not machine code. And how we go about compiling the bytecodes into the native instructions has a big impact on how quickly the system will run, the latency involved, and this speed of warm-up is how long it takes to get to that optimum level of performance. Okay, so what do we do? Well, what we decided to do with Zing was to say, okay, how can we solve this problem of performance in the JVM? How can we try and eliminate the issue of latency that we see introduced by the garbage collector? And that was really our first goal. Rather than starting from scratch and rewriting the JVM completely, what we said was, okay, we need to focus on the garbage collector, but most of the JVM is really good. We don't need to rewrite all of that. There's no reason to do it. So we take OpenJDK as our starting point, and then we make certain changes to the JVM. We use the same libraries, the same tools, and so on. But in terms of the JVM, we make changes to it. We compile that, and then very importantly, we run all of the TCK tests, about 150,000 tests, on the JDK that we produce. The idea behind that is that by passing all of those tests, Zing is a drop-in replacement for any other JVM. Any other JVM that passes the TCK, then you can replace it with Zing, and you know that from a functional point of view, the bytecodes will be executed in exactly the same way. In terms of performance, yes, it will be different, but you don't have to recompile your code, you don't have to change any of your code in order to use Zing. It is simply a case of taking your class files, your jar files, and running them on the Zing JVM, not on the JVM you're using. In terms of what we replace, first thing is obviously the garbage collectors. So we take all of the garbage collectors that are in hotspot, serial collector, parallel collector, CMS, G1, all the others, and we take them all out and we replace them with one that's called C4. Now, another thing that we decided when we were designing C4 was that we would also look at how we could improve things from the operating system level. And that led to a decision, which is that we only support Zing on Linux. The reason for that is that we have things called the Zing system tools. And the Zing system tools, which I'll explain a little bit more in a moment, are about improving the performance of the virtual memory system for the JVM. The second thing that we did more recently was to look at how we can improve the JIT compilation. And again, looking at C2, what we realized was that this was over 20 years old. It was a very difficult piece of code to maintain. It was a very difficult piece of code to modify. So we wanted something that we could use that would enable us to improve the performance of the compiled code. And that's where Falcon came from. And I'll explain all this in a bit more detail. And then the last thing that we've done is to introduce a sort of additional set of technology, which is called ReadyNow. ReadyNow is looking at how to eliminate the problem of warm-up so that you can get to the optimum level of performance much more quickly than you can by letting the code go through all the steps of interpreted bytecodes, then C1 compiled code, then C2 compiled code, and de-optimizations and so on. All of this we'll go through in a little bit more detail. Right, so Zing system tools. As I mentioned, the idea here is to look at how we could improve memory management specifically for the JVM. In the Linux kernel, you have a virtual memory system that maps from the physical pages of memory to the address space and the virtual pages that are used by individual processes. That works very well. It's been developed over many years, but it is designed for general purpose applications. The JVM is a very specific type of application and the way that it uses memory. We allocate a lot of memory in advance for the heap, then we have to do various things in terms of using that memory and the way that we interact with the operating system. So what we decided to do was to introduce a kernel module that would effectively sit alongside the Linux virtual memory system. We would grab a whole bunch of memory and then we could manage it independently for our JVM. This allows us to do some clever tricks, allows us to do various things in terms of caching, what we call contingency memory and things like that, but I won't go into too much detail about that. Now, what we found was that with the shift to the idea of microservices architectures and people deploying into containers and then using those containers in the cloud, people didn't really want to be interacting with the host operating system. What they wanted to do was simply bundle and put their application, their service inside a container with the JDK and the JVM and not have to worry about anything else. So to make that situation work, we introduced since last August the idea of not having to use the Zing system tools by default. So we're using some more modern system calls within the Linux kernel, allows us to do a very similar thing to what we were doing before, get very similar performance, and that means that we get better sort of use of the whole operating system. Now, in terms of the way that works, by default, you don't have to use the Zing system tools. If you want to use more than 1 terabyte of heap, and I'm assuming that in a microservice, you're probably not going to use more than 1 terabyte of heap, although I did have one customer who said that they were using over 1 terabyte of heap for a microservice. Not quite sure they understand microservices, but there we go. So those are the restrictions there. Now, in terms of our collector, it is C4, and that stands for the Continuous Concurrent Compacting Collector. And effectively, that tells you what we do in terms of our collector. So it is, firstly, it's continuous. So it runs all the time in the background whilst your applications are doing their work. Secondly, it is fully concurrent, meaning that we can do all of the work of the collector whilst your application threads are running. We do not need to stop your application threads and pause them in order to do safely the work of the garbage collector. Now, even so, we are a compacting collector, meaning we will relocate objects in order to eliminate fragmentation and to make memory usage contiguous within the heap. So that's very important to be able to do that to avoid excessive fragmentation. But as I said, we can do that concurrently and continuously, hence C4. From a basic point of view, we use some similar techniques to other algorithms. So the first thing is that when we look at the heap space, we actually divide it into 2 generations. So we have a young generation and an old generation. And that makes a lot of sense because if you look at the vast majority of Java applications, most of the objects that you allocate in an application will only be used for a very, very short space of time. If we can collect them in the young generation, we can reduce the load on the old generation. And that smooths things out in terms of the way that the whole system works. Now, we use the same algorithm in both the young and the old generation, and that is a bit different to if you look at the way Hotspot works, because you use one collector for the young generation and a different collector for the old generation, but we use the same one in both. One very important thing about our algorithm is that we do not have a stop the world compacting fallback situation. All the other commercial algorithms at the moment, so if you look at G1 or CMS or Parallel Collector, at some point, they will all say we have to stop application threads and we have to do a full compacting collection on the old generation. And that's where you see those very long pauses, because the time it takes to do that is proportional to the size of the heap, not to the amount of live data in that heap. In terms of the algorithm we use, there are 3 phases to it: mark, relocate, and remap. And all of those phases can be done in parallel. That's good for us because it means that we can apply multiple threads to each of those phases and have them complete more quickly. So how does this work? Well, the thing that we use to enable the kind of core functionality of this is what we call the loaded value barrier. And this is a read barrier, meaning that every time you access an object from your application code, then we will intercept the reference to that object and we will use the object header to determine certain things about what's going on. We use bits within the object header and we can test against those to determine which phase of the garbage collection we're in and also what state the object is relative to that phase. That allows us to enforce 2 rules that do not get broken. So the first of those is that if we're in the marking phase, every object that you get a reference to in your application will be marked as in use. And that means that it will not accidentally be garbage collected because we haven't gone through a remarking phase or anything like that. We don't need to do that. So we guarantee that every object reference you get will be marked as live data, so it will not be garbage collected. Second thing is that if we're in the relocation or remapping phase, then we guarantee that the reference that you get in terms of where the object is in the heap will be correct, meaning that if you make changes to it, those changes will not be lost because we're in the process of moving the object, and therefore you get inconsistent data. So it's a very safe way of being able to do concurrent marking and concurrent relocation. People often say to me, well, hang on, if you're going to intercept the read to every object, we do that a lot. So surely that's going to degrade the performance overall of the JVM and the application. And the answer to that is, well, yes and no. So yes, technically we do, because we introduce a small overhead, but because we're using bits in the object header, essentially all we're doing is two instructions, which is a test and jump. So we test the bits, and then if we need to do something, we jump to a handler routine and we do something. But the majority of the time, we don't need to do that because there's only certain situations where we would need to do things. So most of the time, all we're doing is testing and saying, yep, no, that's okay, and move on. If you look at what that equates to in terms of the way that the processor works, it's a single micro operation on an x86 architecture, and that means that you're looking at less than 1 nanosecond of overhead per read of an object. If you do that enough, sure, you will see some degradation in performance, but comparing that to the time it takes to reference data in L2 cache or L3 cache or main memory, that's going to be far more significant, and so you won't notice any overhead in terms of the use of the loaded value barrier. Now, how this works is that when we need to start running the garbage collector, so we're running continuously, and the garbage collector will decide that it needs to do some work. So we start off, and again, we use a similar approach to other algorithms, which is we create a root set. A root set is a list of all the objects that you have directly accessible from your application code. We scan the stack, we look at the registers, we look at the static variables, and we build up a list of the objects that we can reference. Clearly, those objects are most likely going to have references to other objects. So we need to trace through from the root set to all the objects that are accessible and create a graph of our accessible data. So the garbage collector will start doing that. It will work its way through the root set, and it will set the bit to indicate that that object is in use, and so it's marked. We then follow the links from that object to other objects, and we mark those objects because they're still in use. And we can do that through the whole tree or the whole graph of objects that are accessible. Because the root set has independent pieces of data, we can apply multiple threads to this. So we can do it in parallel. There's no contention, there's no issue there. Our application threads are running at the same time. So at some point we may access an object, and we use our test and jump, our loaded value barrier, and we say, is the bit set to indicate that this object is still in use? If it's not, then we jump to a handler which says, okay, let's mark that object as being in use, and then we can return it to the application, and we guarantee that it is marked. Obviously, what we need to do is also trace any other references from that object to the ones that it uses and make sure that all those objects are marked as well. So we don't want to do that in our handler because technically we're doing part of the garbage collection work in the application thread context. If we started tracing other objects, that would be an unbounded task, and it could take quite a long time. So to get around that, we then pass that object to the garbage collection threads and make it part of the root set, so that the garbage collector can then trace those objects and deal with that. But any other references that we trace or use from our application will also be marked. So that enforces our first rule. The second thing we do is our relocation phase. And in this case, what we've got is objects spread out through our heap where we've got gaps between them because some objects are now no longer in use. So we've got 5 objects in our heap here, A, B, C, D, E. And we want to relocate those into another part of the heap so that we can compact them. And we do that very simply by calculating new references for where those objects are going to go. A goes to A prime, B goes to B prime, and so on. We can copy those objects in order to effectively move them. So we copy the data from A to A prime, B to B prime, and so on. To do that safely, we put a lock around the actual copy. Now, that would introduce, or does introduce, a pause, but it's a very, very short pause because most objects are very small. The time it takes to copy a small object is going to be very small. So the pause that you would see is going to be very negligible, really. In addition to copying the objects and relocating them, we also create a side table which contains a list of which objects have been moved from where to where. So we now know that A has been moved to A prime, B has been moved to B prime, and so on. Then we come to the remapping phase. In the remapping phase, our garbage collection threads come along and they say, okay, we need to work our way through the side table here, and we need to update the references that we have in the object headers. So we look at A and we say, okay, let's relocate A to A prime, change the reference, and then set the bit in the object header to indicate that that has been updated. And again, we can do that in parallel. We can have multiple threads doing that work because the data is independent. Our application threads are still running. So at some point we may access an object and we use our test and jump again. And this time we're going to say, the bit has not been set to indicate that that object has been updated, or the object header has been updated. So again, in our handler, we will do a very small amount of work for the garbage collector in the context of the application thread, and we'll reference the side table, we'll update the reference of the header, set the bit to indicate that it has now been updated, and return that to your application thread. So now it has the right reference and you can make changes to it quite safely without any fear of losing or corrupting your data. What this gives us is what we call the pause-less compute collector. And the most important thing about this is it gives you a very consistent latency profile. So the latency is unchanged regardless of certain things. First of which is heap size. So we can scale all the way from 512 megabytes up to 8 terabytes. And I believe we're at the point where we may even be able to go up to 20 terabytes of heap space very soon. But we can scale very much up to 8 terabytes at the moment. And the pause times, the latency of the collector will not change. Similarly, in terms of allocation rate, that won't affect the pause times. How long you run this thing for won't change. Memory fragmentation, load profile, all of which are irrelevant in terms of how long the garbage collector has to pause in order to do its work. Talk very briefly about GC tuning because this is quite important. A lot of people spend a lot of time trying to tune the garbage collector to eliminate the problem of pauses. And the reason that they spend so much time doing this is because there are lots of options. If you've ever looked at the -XX options that are available in the JVM, there are literally hundreds of them, and dozens of them apply to different garbage collection algorithms. And just taking two examples here, these are real-world examples we've taken from customers where they've set up a variety of different parameters to configure the way that their JVM starts up and the way the garbage collector works. Now, I won't go through all of this, but I just will highlight one thing, which is both of them set the survival ratio. The first one set it to 128, the second one set it to 2. And the question is, well, what's the right value? And there is no easy answer to that. Mostly what people do is they say, well, okay, let's try changing the survival ratio, and they set it to a particular value. They run their application, they benchmark it, then they try changing the survival ratio and see, does that improve it or does it degrade performance? And you have to do that a number of times until you find a value that seems to work for your application. And then you've got to hope that nothing changes in your application. And the other thing that you have as a really big problem is that's only one parameter. And there are literally, like I say, many parameters that you can change, dozens of parameters. And so you end up with an n-dimensional space that's very, very difficult to solve in terms of the optimum set of values. Let's look at the equivalent set of parameters if we use Zing. It's just that. Literally, all we do is set the heap space. And that's our initial approach. I mean, we've got about maybe a handful of other options that we can set, but these are fairly straightforward. They're ones that we understand very well, and it's easy to kind of say, okay, well, if we want to do this, we can do that. But what we tend to do is simply change the heap size. So we set a heap size, run the application, make sure it works, then we reduce the amount of heap size we give, make sure it still works, and gradually bring that down until we get a point where it starts to not quite behave the way we want it to, and then we just bring it back up a bit so we know we've kind of got enough room to keep the application running. And that's all there is to it. So how can I prove to you that this actually works? Well, what we've done is to create a small open source tool called JHiccup. And JHiccup is designed to measure the latency associated with the JVM and everything below it. So it has nothing to do with the latency of your application, how long it takes you to process a transaction within your code. It's all about what is the latency of the JVM, the operating system, the hardware, and so on. And the way it works is we put a thread alongside your application, but it doesn't interact with the application, so there's no recoding or anything like that. And to minimize the effect on the performance itself, Heisenberg's uncertainty principle, what we do is spend most of our time asleep. The JHiccup thread will go to sleep for 1 millisecond. When it wakes up, it looks at the system timer, system clock, and says, I expected to wake up 1 millisecond later. What time did I actually wake up? And it can use nanosecond resolution so we can get very accurate results on this. And so if we're running on hotspot and we get a 20 millisecond garbage collection pause, then obviously we'll wake up 20 milliseconds later than we thought we would. We can record that information, produce some histogram log files, and then get some nice graphs. Here is an example of a nice graph. So on the left, I've got hotspot running. On the right, I've got Zing. Now, this is an Elasticsearch system. It's running on a reasonable 128 gigabyte heap. And if we look at the hotspot graph, what we see here is the latency associated with the JVM and the operating system. And we see a very typical hotspot graph. There's a lot of small spikes that we can see there, and that's minor GC pauses. And then we've got two bigger spikes, which is major GC pauses. If we look at the graph for Zing, you look at that and you might think, well, hang on, so big spikes is bad. And what you've got there is a lot of spikes, and there's some quite big spikes there, and it's all very random, and I don't really see anything that makes me think, wow, that looks really good. Haha, but I have been very deliberate here. I have misled you. And what I've done is I've set the scale of the graphs to be different. So on the left-hand side, the hotspot graph goes from 0 to 8 seconds, 8,000 milliseconds, meaning that most of the minor GC pauses are about half a second. The major GC pauses are 5.5, 6.5 seconds. On the Zing graph, I've scaled it from 0 to 80 milliseconds, meaning that most of the pauses we're seeing there are in the sort of 10 to 20 millisecond range. If I set the scale of the graphs to be the same, suddenly we see how Zing works. We can eliminate all of the garbage collection pauses and the issues of garbage collection affecting our application. Now, remember, this is run on exactly the same machine, so we didn't change machines or anything like that. All we've done is change where the JVM gets picked up from. Same application, same workload, everything exactly the same, just the JVM is changed. Okay, now let's talk a little bit about JIT compilation and how we can improve that. So as I said, when we started looking at this, we thought, okay, let's replace the C2 JIT compiler. What can we do? And again, we didn't want to start from scratch. So we found this project called LLVM. LLVM is a very good open source project, been around for quite a long time. And it's mostly focused on the idea of providing the best possible back end of a compiler. Typically sort of focused on C and C++ code, could be other programming languages like Go or ones like that. But it's about taking intermediate representation code and then providing the most heavily optimized code based on profiling information and so on. So we took that and we integrated it with the JVM as part of a JIT. And so that obviously involved quite a lot of work, making it work in that environment. We contributed those changes back to the project so that other people would use that if they wanted to. What this allows us to do is get much better performance out of the code that's generated. We can use more speculative optimizations, we can get better intrinsics, more method inlining. So how does that sort of provide real world activity? So the first thing here is that if we look at a simple piece of code like this, so I've got a loop that goes through an array, adds up the values in that array. Any modern compiler will look at that and say, I can use vector operations to improve the performance of that. And a vector operation is where you use a very wide register, 128 to 512 bits, and you load up multiple elements of your array, into that wide register, apply a single operation to all of them in one clock cycle. So it's single instruction, multiple data. So modern compiler does that, all very good. However, if we make the code a little bit more complicated, so we introduce the idea of conditional, we introduce the idea that we only want to add one element of an array to another element of an array if one of them's even, then it gets much harder for compilers to recognize that as something that can use vector operations. And in the case of hotspot, it won't recognize that, so C2 won't recognize it, Falcon will. And if we look at the code that's generated, so we take that exact piece of code and we compile it on C2 and look at the resulting native instructions, what we see is, don't worry about all the details of this, but the red boxes show that effectively what C2 is doing is trying to optimize it by using loop unrolling. And the only thing that it's really doing here is doing a double iteration or a double process on 2 elements per iteration. So it's a very minimal improvement in terms of performance. If we look at the same thing with Falcon, then the code looks a lot more complicated. But what's actually happening here is that we are using vector operations. We've recognized that we can do that. And so we can apply vector operations to it. On this particular machine, it's using AVX2, which is a 256-bit wide register. And it's doing loop unrolling, but it's doing 4 elements per iteration. So the overall effect is that we can do 32 elements per iteration, and a number of those are done in parallel, so we get even better performance on that. And that's just one example of what we can do with Falcon. Falcon's much more modular. It's much easier to add optimizations to the code, much easier to get things to change to improve the way that the code is generated. Last thing to talk about is ReadyNow. And obviously we've seen the graph already, where we see that it takes time for the application to warm up. We're all used to that in terms of Java. And the problem is that every time we start our application up, we have to go through exactly the same process. So we have to go through the interpreted C1 compiled code, profiling, C2 recompiling, de-optimizations, blah, blah, blah. What we don't want to do is do that every time. So we came up with the idea of ReadyNow. And essentially what you do is you run your application, you let it warm up to the optimum level of performance, and then you say, okay, let's save a profile of that application. The profile consists of 4 pieces of data. All the classes that are currently loaded, all the classes that are currently initialized, the profiling data that was collected from the C1 compiled code that was running, and most importantly, any speculative optimizations which resulted in a failure and therefore had to be de-optimized and recompiled. What we can then do is take that profile at any time. So we don't have to, we could wait 2 minutes, we could wait 2 hours, 2 weeks if we want. Then we can use that profile the next time we run the application. And rather than having to go through the same process again, what we do is we load all the classes we can, we initialize all the classes we can, and then we compile most of the code that we need for all the methods that were compiled before we start executing main. So the point you get to your application code, you're literally going to be running at about 98% of the performance you had when you took the profile. Last 2% requires us to do 1 or 2 transactions to be processed just to kind of get to that 100% point. This also leads to a significant reduction in de-optimizations, which is a very big performance improvement. So if we look at the idea now, how we would see our graph in simplified form, if we do that without ReadyNow, then we've got this warm-up slope, which takes time, and then we get our optimum level of performance. With ReadyNow, we get a much steeper graph, but we've got this kind of blank bit before where we're doing all the work we need to do before we get to our main entry point. And that obviously could be a bit of a disadvantage. So we want to try and eliminate that as much as possible, because that's where we do our class loading, initializing, and compiling. So what we've done now is what's called compile stashing. When we collect the ReadyNow profile, in addition to those 4 pieces of information, we also record all of the code that was compiled during the run of the application. When we restart the application, we know that the Falcon JIT compiler is fully deterministic, meaning that if we take the same method, same bytecodes, you haven't recompiled it, and the same profiling parameters, then the result in terms of the code that's generated by the compiler will always be the same. So we can reuse that So we use that fact so that if we have the same method that needs to be compiled and we have the same profiling parameters, then we don't actually have to recompile it. We can simply use the code that we had from the previous run. And that avoids a lot of costly compilations as the JVM starts. So now we go from the idea of without compile stashing, we've got this blank spot at the beginning where we're not doing anything. And now we can reduce that by up to 80% in terms of compile time and up to 60% in terms of CPU load. So just to summarize about Zing, essentially what this allows us to do is to change that graph. So we can move away from the less than ideal graph, the real world graph, to much more like the ideal graph that we're after. And essentially, there are three parts to that. First is C4, which eliminates the garbage collection pauses. Falcon actually raises the level of optimum performance that we can get. And then ReadyNow is about pushing that graph out so that we can eliminate as much as possible the warm-up phase associated with the application. So what we do is we say with Zing JVM, it's all about start fast, go faster, and stay fast. So consistent latency, consistent throughput, and even under demanding changes in load, doesn't matter. Very important thing is it is a simple replacement for other JVMs. No need to recode, no need to recompile. If you're interested in finding out more about this, if you're interested in giving it a try, then if you go to azul.com Zing trial, then you can get a free 30-day trial of Zing, and you can actually, generate your own graphs that show how you can eliminate garbage collection, show them to your boss and go, look, this is what we need to solve our problem. So with that, I'm going to hand over to Dennis. So I'm going to stop sharing my screen, and hopefully Dennis is still here. So he will start sharing his screen.
All right, hold on for a second. I'll be driving the rest of the presentation. Okay, folks, I think that Simon has shared all the details you need to know about Zing, so that right now we can proceed with Apache Ignite. But before talking about Apache Ignite as one of the components of this low latency system solution we are reviewing today, I want to introduce you to the case study, to the actual test that we performed to compare our solution with C++ based solutions, as well as to compare Azul Zing with with hotspot virtual machine. This benchmark, this test is real. It's being used by one of the well-known banks to validate performance and latency of the system that is running in production. And that system, what it does, it actually kind of processes payments, and it performs the latest step when you need actually to update your bank accounts, either debit or credit them. But also one of the guys, like Matt in the discussion chat window mentioned that, in fact, when it comes to the overall payment process, usually many credit card issuers and banks, they give you like 10 seconds or like 500 milliseconds. It depends. And here is, yes, I need to clarify that usually this process is a multi-step one. Whenever we, as a consumer, do any payment, we just slide the credit card, but then behind the scenes, we have a lot of different agents and parties involved. Some of the players that will process your transaction would need to do fraud detection. Some of them would need to do the final payment processing by crediting or debiting a bank account. So right now we are going to talk about the final step, when you are going to when you need to read bank accounts of your customers, and then you need to update them with the new balances. So payments benchmark. What we've done, we deployed 3 nodes Apache Ignite cluster on AWS, and those were machines. Every cluster node, we are given a dedicated 6x large virtual machine of AWS. Overall, what we've got, we had 72 cores cluster-wide across all the 3 machines, and we were given 600 GB of RAM and 45 terabytes of disk. What were the tested scenarios? First of all, we were comparing Azul Zing C4 and hotspot G1 We were comparing, we executed this benchmark, and we are doing this testing for a long while, and we checked Shenandoah garbage collector, but that time it did not show performance results comparable to Azul Zing. I do believe that the things might have changed prior to this point, but that's something that you can explore on your own if you're interested. What we were testing, what were the configurations? First of all, we would load 200 gigabytes of data in this cluster, and then we would run different transactions. I will show you how those transactions look like on the next slide. Then, with the real use case, nobody in his or her sane mind would take a pure in-memory system in production, because that system can go down for due to different reasons. That's why you would need to have a copy of the data on disk. That's why the second scenario would be having the same copy of the data on disk in Ignite native persistence. And the final use case, if you recall that example of Southwest Airlines, that could preserve the same number of routes for their flights, but still be able to sell one of the jets and pay off their bills. We also would try to preload 3 times more data into the cluster, but then instead of scaling out this cluster, we would see how well it can perform only if 30% of the data is kept in memory. All right, speaking about the workload, when I will be talking about an individual transaction, when you will be seeing those charts and histograms, every individual transaction accesses at least 20 records, like accounts of balances. We will be comparing distributed transaction rates. That's what the test does. The throughput is 1,000 operations per second. And for the reads, our target latency is 50 milliseconds for 4/9 percentile. And when we are talking about 15 milliseconds, we assume that what's included? You have your application, you have your cluster. Application sends this transaction that accesses 20 records, and this 15 milliseconds involve the network round trip. It involves, going to the cluster nodes, reading data from memory or from disk, and bringing back to the application. You need to stay within this 15 milliseconds for the whole operation, including network and everything in between. For transactional updates, we need to sustain, our system needs to sustain 2 times more updates, 2,000 updates per second, but the target latency is not that harsh. We are given 50 milliseconds for 9th percentile. And finally, here is another worth noting remark. When we are talking about updates, if I store my copy of my bank account on Ignite cluster node, there will be always a primary copy of my record. And for the sake of high availability, there will be a backup copy of this record. So whenever I will be updating any account, it will involve the update of primary copy and backup copy as well. And that's all need to fit into 50 milliseconds. And we used the following tools for measurements related to the Java virtual machine. So the very first benchmark, the case when we just went ahead and preloaded, just a small fraction of data, 200 gigabytes in our 3 nodes cluster. Those were the first results. We are talking first about the transactional reads. To the left, you can see the histogram for hotspot G1, and to the right, we have Azul Zing running with C4. This here is, I'm misleading you a bit because the histogram is not scaled. And if we equalize the scale, those would be the real numbers. And here is to remind you that was the target latency. So again, 1,000 reads per second. Each read is a transaction, and each transaction accesses 20 distributed records. When it comes to transactional updates, here is the things that are a little bit more interesting. Again, if we equalize the scale, that would be the chart. We are given 50 milliseconds to complete this in time. And here is, I would say that hotspot as well performed really well, but unfortunately, closer to the end of the benchmark execution. This benchmark is usually executed for 2 hours at least. We've got a couple of spikes. And that's the point of why, when we're talking about latencies, we also need to keep in mind that the latencies need to be reliable and consistent. At least with Azul Zing, C4, we could confirm that we are getting low latencies, and those latencies are consistent. All right, like something for beginning, right? That was the case. And next, before we look at the other benchmarks, other numbers, and we get that to the Q&A session, let me quickly introduce you to Apache Ignite so that you understand why we selected this system for low latency use cases such as payments processing or fraud detection, or Ignite as a system for your 5G infrastructure. So before, I do believe that many of you guys have already seen this table. That's not my invention. I borrowed it from the internet. Some smart guy decided to come up with this table that shows how various system events are different in terms of latencies. So what we are getting, what we can see in the very first column is a specific system event that needs to be processed by our CPUs. In the column in the middle, what we are seeing is the actual latency time. How much time does it take for our CPU core on average to complete that operation to the left? But you know, we as humans, for us, it might be hard to perceive and comprehend how big is the difference between nanoseconds or microseconds and milliseconds. That's why the author of this table introduced the last column, so-called computer latency at the human scale. What the author did, he actually assumed that let's equalize 4 nanoseconds to 1 second, that's the one CPU cycle, and then we can do the same translation for the rest of the operations. And once we do this, we can pay attention to the following system events. These system events show that main memory access latency is like on average 100 microseconds, while SSD I/O is somewhere in between 50 and 150 milliseconds. And like it might be, you know, that not that big, but when we are thinking in the terms of our human scale, it's like the difference between minutes and days or even months. That's primarily why many storages and backend systems right now are designed with memory as the storage, as the primary storage for your data. Because of that, it's performance. And then the second reason is scale. Many systems, let it be not only Ignite, but we can talk about caches like Redis, we can talk about databases like MemSQL or VoltDB. All of them keep this in mind. That's like just the latency time. But our platform of today is Apache Ignite. So Apache Ignite is a memory computing platform powered by Java. That's a Java middleware, if to put it simply. That's like a holistic representation of Ignite. But in fact, I define Ignite, when I'm talking about Ignite, I define two primary components. The very first component is Ignite multi-tier distributed storage. By definition, Ignite can keep data in memory. That's why it goes with a memory tier. But also it can persist all your records and indexes on disk. And here is with disk, we have two options. The first one is Ignite can integrate with your external databases. The most common integration is Ignite with relational databases, and those can keep your on-disk data. Or also you can select and go for with Ignite native persistence. The next slide will explain you why would you have these two options and why would you select either of them. And on top of this very first component, which is the multi-tier distributed storage, Ignite provides a variety of different APIs needed for our applications and our services. We have key value, we have standard SQL, you for sure can run transactions. Also, why the beauty of as a Java middleware, Ignite allows us creating our custom Java compute tasks and execute them on our server machines that store actual data. That's the feature available as part of a compute grid. We will talk about it. So everything you see in the middle in red is available in open source. It belongs to the Apache Software Foundation, and it's just go and take it. To the left and to the right, you have enterprise features provided by GridGain. GridGain is one of the major contributors to Ignite and to the Apache Software Foundation. GridGain originally donated Ignite to the foundation, but still it stays in one of the most influential and contributors who believes in open source, and we kind of, most of the functionality is available in Ignite, I would say this way. How Ignite is being used, folks? Because that's just the previous slide shows us a collection of different building blocks. It's our Lego constructor. But I would define three primary use cases how Ignite would be deployed in production. The first one is Ignite as a cache, then Ignite as a database, or Ignite as a component of so-called digital integration hub architecture. The very first use case, the most simple. Here is you might have troubles with your databases performances, or you need to boost some of your applications, and just you can go ahead and deploy Ignite as a distributed cache. Such a cache would also be able to write all the changes to your underlying databases for you automatically if you need it. And also that's a distributed cache that supports transactions, SQL, or compute and machine learning APIs. The other use case that is getting more dominating is Ignite as a just in-memory database with its own native persistence. The only difference here is that instead of persisting all the changes in an external database, you would enable Ignite native persistence. Why would you do this? So why Ignite native persistence and not, let's say, Oracle for this use case, for the greenfield applications built with Ignite? Ignite native persistence goes with two crucial capabilities. The very first one, if you have it enabled as a persistence tier, then you do not need to cache all data in memory. All the data always will be located on disk, and then depending on your memory capacity, you can keep 100% of the data in memory or only a subset of it. That's an exception that works well for IoT applications, for analytics, etc. When you don't want to keep some, historical data in your memory space, you don't want to waste it. And the other use case, as long as you Ignite can read all the records that are not available in memory from disk automatically. If your cluster is restarted, you don't need to wait while all the data is brought back in memory. And that can help you to significantly shorten the downtimes, possible downtimes of your cluster. Because what happens with many memory systems, if you start storing, let's say, terabytes or petabytes of data, then let's say if your cluster needs to be reloaded, it can take you hours and many hours to reload the data, and that can be significant downtime for your business applications. If to tell you a story, just how this native persistence was developed in the very first place, it was requested by one of the customers of GridGain, and then GridGain just developed it together with Ignite, making it open source. But the customer was a pretty well-known bank, and they selected Ignite and GridGain as their primary in-memory computing platform for various applications, including payments processing. But then they had another requirement that was pretty unique those times. They were saying that, guys, we have a strict regulation requirement. If our banking system goes down, then we need to recover in 3 minutes. We have only 3 minutes to make all the system operational. And they are storing terabyte, like right now, one petabyte of data in Ignite and GridGain. And there was no way for them to preload a petabyte of data, let's say from Oracle to Ignite within 3 minutes. That was not enough. And that's why originally this native persistence was developed to challenge those use cases when the possible downtime can be minimized as much as possible. But right now it's used like everywhere. And the final use case is Ignite as a component of digital integration hub architecture. So here is what's the difference. You might have different disjointed databases. Database A can keep accounts of your customers. Database B can keep historical data related to visits to your website. And you might have some applications that need to get and to read all this disjointed data because there are some new services that are being built. You need to do analytics, etc. And Ignite here is selected as a centralized, shared, distributed storage that keeps data from various databases, not all the subset, just something that needs to be accessed by all the applications. And then those applications can connect to that shared cluster and read data using all the APIs of Ignite, etc. Speaking about Apache Ignite, just to finish this presentation, Ignite, those of you who are not familiar with it, is one of the top 5 projects of the Apache Software Foundation. In the foundation right now, we have 350 top-level projects, including Kafka, Cassandra, Hadoop, etc. And we are ranked as the 2nd most active in the dev list activity. There are many contributors to the project who not only use, but also develop Ignite. And we are the 3rd most active project if to judge by the user list activity. A lot of application developers are coming to Ignite. They certainly have issues, questions. They want to get some of the design considerations in more details. So right now, let's talk about internals. So Ignite, let's take an individual Ignite cluster node as an example. Yes, we run on JVM, but we do not use Java heap as our primary storage for your application records and indexes. In fact, we use our off-heap memory as a permanent storage for your data. So why we came with this conclusion? Because Ignite, by definition, is quite agnostic to a virtual machine it's being running on. Yes, for low latency use cases, we determined that Azul Zing is the best, is the JVM of our choice. But also there might be, other use cases when you're using hotspots, when you're using GraalVM, etc. And off-heap allows us to use all the memory capacity of an individual box. So we have customers and users who are running a single cluster node on a machine having 7 GB of data, 700 GB of data, or 1 terabyte of data. And Ignite can easily digest all that memory space by using our own off-heap memory. But also as a Java middleware, we always use Java heap to store objects generated by your applications. We copy data from off-heap to Java heap whenever we need to prepare a result set for your SQL queries. Your computations can generate application objects that will be located in Java heap. And what we discovered throughout many years of working with many banking and telco companies is that low latency systems, they are not just impose strict requirements to your latency time, but also they can boast about high throughput queries. They usually run thousands of iterations per second, and that would lead to that can easily over-occupy Java heap size. And we're looking for a garbage collector that would be able to do this garbage collection in real time, constantly, not affecting the latency time. So that's how the representation memory structure of an individual cluster node of Ignite looks like. And then, guys, whenever you need to scale, you just scale. You need more memory space. You need more CPU cores. You just scale out your cluster, throw in more cluster nodes. That's what you do. A couple of words about native persistence. This native persistence, you can think of it as of a classical disk-based database. It goes with write-ahead log files. It has checkpointing, process, etc. And what the diagram to the right shows, let's take this use case. Your application sends an update to a cluster node. This cluster node will immediately update an in-memory copy of your record. And also it will mark this in-memory copy of your data as a dirty page, as dirty, that needs to be written back to disk. But before writing it back to disk to the partition files, it will write through this change to the write-ahead log file of this cluster node. And then it will respond to your application saying that, all right, this update happened, so please proceed with the rest of your application logic. And then in the meantime, whenever a number of these dirty pages, dirty records grow significantly, or when some other parameters kick in, Ignite node will kick off another cycle of checkpointing process. What checkpointing does, it will traverse through all the dirty records in memory that were updated in memory but not on disk, and it will flash all those changes to the partition files. Partition files store the final actual copy of record on disk. Why do we do this? First of all, if any record, if you do not have enough memory capacity to keep all the records in RAM, then Ignite will read the latest value of your record from the partition file for you. It allows us to trim the size of the write-ahead log file. As soon as the last checkpointing cycle is finished, we can trim our write-ahead log file. We no longer need it. And also, if you do any cluster restarts, the shorter your write-ahead log file, the faster would be your restart. Because if the write-ahead log file has nothing inside, it means that all your partition files are consistent. And once the cluster is interconnected, it becomes operationable. If we need to replay our write-ahead log files, making the files consistent, then it will also contribute to the startup time of your system. We need to kind of traverse through the write-ahead log files and to apply all the changes to the partition files. That's why we do this checkpointing process in background all the times. So right now, folks, you know how Ignite in memory structure looks like, and you know why we have Ignite native persistence. So let's run the same test. 1,000 transactional reads per second with 50 milliseconds latency, and also 2000 writes with 50 milliseconds latency. But right now, in addition to in-memory copy, we would have a copy on disk. So with reads, when it comes to reads, I wouldn't say that the graph changed a lot in here. Again, that's the result we've got with Azul Zing. We did not note any changes after enabling persistence with J1. Yep, we've done a bit more optimizations, but still we were not able to stay with to comply with the requirements for 9th percentile. When it comes to the updates, here is we expected to see that it would kind of will give more troubles to Azul Zing, but in fact, like with the current data size and with the current high throughput, everything was all right. So we were able not only update in memory copy, but also we were writing all the changes to our write-ahead log files, and also in background throughout those 2 hours of the benchmark, we were able to perform many checkpointing cycles, updating our partition files on disk. And the final use case, again, going back to that Southwest example presented by Simon, when we decided, to demonstrate and to confirm that this whole system solution can scale out, we decided to let's do this. Let's triple the data size, but let's not scale our cluster. Let's see how much of the given cluster capacity we can use for this specific payments processing test. And to do that, we were able to use only 30% of our memory space, meaning that for 70% of the requests, the data were retrieved from disk, and Ignite served the data from disk, not from memory. So that's the chart. Again, let's equalize it. Let's remind us the target latency. With Azul here, finally, we were able to see that for 100% of operations, we were not able to keep the target latency, but for the requested for 9th percentile, we were okay. And when it comes to the updates, here is we were updating a lot of the data. Again, the same story. 100%, we were not able to meet this 50 milliseconds latency for 100% of operations for Azul Zing, but for 9s, no issues. We stayed within the requested boundary. Okay, guys. And finally, I want to finalize my talk also to explaining you how the cluster stores the data in a distributed fashion, and also why do we need MapReduce or compute APIs of Ignite. That benchmark that we've shown to you talks about the payment processing phase when you need basically to read your bank records and you need to update them, when you need to read your bank accounts and you need to update them. So right now, let's talk about another phase that also always takes place whenever you swipe your credit card. Let's talk about the phase when a bank or a credit card issuer need to validate your payment. They need to do various fraud detection verifications. So usually in my experience, many banking systems, they use mainframes. And mainframes, it's a perfect solution for credit card payments verification, like for fraud detection verifications. Why so that? Because, let me switch. Okay, because the way the system is designed, it stores all the transactions history in sequential files. So whenever a request to this mainframe arrives, it can validate all the, it can do all the verifications almost instantaneously. By default, and that might vary from a bank to bank, but what I've seen is that some of the companies, they need to calculate thousands of variables, of fraud detection variables, to either reject or accept our payment. And to calculate those thousands of different fraud detection variables, they are traversing through the 1,000 latest payments done by you as a customer, and also through the history of a merchant where like from whom you're buying something right now. So in our use case, let's say that I'm buying a cup of coffee from Starbucks, and then this kind of request finally arrives to this mainframe that needs to complete this payment verification phase. What the mainframe will do, it will open transaction history of my account. It also will open the transaction history of Starbucks. That includes not only my payments, but also payments of Simon, let's say. And it will be running and calculating like thousands of different variables in parallel. And then, depending on the outcome, this transaction would be either approved or not. So how do we tackle this? How would we design our system, considering that our data will be distributed, and considering that we need to, whenever we are doing fraud verification, we need to iterate through thousands of, through the history of our accounts and payments, etc. It's not that good to use classical approach when our application would go to the cluster and would read that history to the application layer, does all the verifications, and then responds. There is no way you can do this within like 50 milliseconds or 20 milliseconds. It's too much. So that's why we need to keep in mind two technical tricks when it comes to distributed systems such as Apache Ignite, but also it applies to other distributed systems. First of all, you can store your related data together. In Ignite, we call this feature affinity-based data distribution or affinity collocation. What we have here, let's say that I have accounts table. Simon's account is placed on one cluster node. My account is located on another machine. And also we have transactions. And with affinity-based collocation, technically, the cluster can have and store all the payments of Simon, the history of Simon account on the same cluster machine. And that's good for us. And the same applies to my account. So we do one special configuration in Ignite and you're good to go. You can achieve this distribution out of the box. Also, but when it comes to the, let's say, to the step when you need to calculate those variables and confirm whether this payment is fraudulent or not, you cannot just bluntly move my history or history of Starbucks or another merchant from the cluster to the application. It will not work. You will not be able to complete this with a decent performance time. That's why with Ignite, you can do the following tricks. You can use our MapReduce framework. We call it compute grid. You basically develop your compute tasks, and you can compute tasks what it can do. It can do this whole calculation. It can traverse, it can open, it can access your tables, accounts, transactions, and history. It can traverse all the local data on the cluster machines. And then it can just respond to your application saying that whether this transaction can be approved or not. That's a classical MapReduce paradigm. So most of you are already familiar with this. Many of us had experience working with Hadoop and similar systems. And Ignite is another exception here. You create your task, you schedule it for the execution, it executes on your cluster nodes that store actual data, and then those cluster nodes respond to your application that can decide what to do next, depending on the response. And why would we care about that, guys? Why would we do all these optimizations? Why would we store related data together? Why would we use compute tasks for applications when we need to traverse through the history of payments? The question is obvious. If to jump back to this table that we used, to show the difference between main memory accesses and disk I/O. Yes, main memory is faster than disk, but disk access is much faster than network. That's why if your application if your application that is connected to Ignite starts using network excessively, if it invokes data shuffling a lot, then you can just lose all the benefits of your memory cluster, because the network will kill your performance advantages. That's why keep in mind that collocate your data, use compute tasks when you need to traverse through large data sets, etc. There are many other techniques. Just keep this in mind. It's all about performance and latency. And right now, if we try to upgrade and update our system to the Ignite cluster, it will look like as follows. Let's say that I have like several nodes clustered, and then what would happen? My transaction history will be located on one node. Simon's transactional history might be located on the same one on a different node. It doesn't really matter. But when it comes to the Starbucks transaction history or any history of another merchant, here the situation is a little bit tricky, because my history is small, right? I'm not a pretty good consumer. But Starbucks, like millions of people are buying from Starbucks, and there is no way we can keep the history of Starbucks on a single machine. Otherwise, unless that's like every cluster node is a mainframe, but like what's the purpose of that? That's why you can split your history of Starbucks into chunks, and those chunks can be stored on several machines of your cluster using all the memory and disk capacity. And so right now, if I meet all the other intermediate steps that are involved whenever you're doing this payment, and to focus on this fraud detection task, whenever you do this transaction approval request, the cluster node that stores my bank account will receive this request. It will see, all right, that Dennis's transaction history is here. It will access this table. It will start traversing through the local data. And also in parallel, concurrently, it will see that, all right, Dennis is doing the payment at Starbucks right now. Let's calculate like several variables based on the Starbucks transaction history. And that node will also send the request to the other node that stores the second chunk of Starbucks. And both nodes in parallel will be calculating all those fraud detection variables. And once this is completed, you are responding back to your terminal. Or like I think that here we need to show that once this verification is completed, then you need just to accept this payment. You need to debit, like you need to credit my bank account, etc., and then you need to debit Starbucks account, etc. But that's something we can omit for now. So as a summary, when it comes to the predictable and consistent latencies, here is for sure, like, as it was said, we tested and we used and we keep using this solution for low latency systems. And when we are talking about low latency systems, it's not just about the latency at the moment. That's about the latency, predictable and consistent latency. We want this latency to span through, like, you know, the time. It's not just, you know, that we show this small latency for now, and then the latency will not be as good as it was before in a couple of hours from this moment. Also, with ultra low latency and high performance, all right, use whatever you have, but if you have an ability to use your main memory as your primary storage, go for it. Even if it will not be Apache Ignite, right? Something else. Check this out. You just keep in mind those tables that show actual latency and human latency. Keep this in mind. If it's possible, select any memory-based solution to achieve the lowest latency and highest performance. And finally, when it comes to the horizontal scalability, with this presentation, we showed you, you know, just, you know, something probably that is negligible when it comes to a distributed world. We were operating on the data size measured in like 200 gigabytes, 600 gigabytes. But like, it's whenever you need to scale, just scale. Scale out linearly. The purpose is that your system can do this. So how and when you can learn more? So first of all, a couple of useful references for you. Go to Azul Zing website, technology to Azul website if you want to learn more about Zing and all the features covered by Simon. And also if you want to learn and experiment with Ignite, that's the website that is located on the Apache Foundation domain. So having said that, let's jump to the questions. I do believe that we have many. And while guys, we are working through the questions, still as a reminder, you can take part in this raffle. We are kind of have these books, and actually these books are recommended. That's not the books out of my mind or Simon's mind. Those books are recommended by Apache Ignite committers, those who develop Apache Ignite, and all of them, most of them have already read this book. So if you wanna see what people read, people who develop databases read, you can also see what's useful. All right, thanks.
Hi, thank you very much, Simon and Dennis. Very enlightening presentation. So we had a few questions that were coming in on the chat. I captured some of them. There was a question about Hazelcast. So somebody mentioned that they were using Hazelcast in their previous place, and versioning objects in memory without downtime was a huge issue. So how does Ignite resolve this problem?
With Ignite, we have native persistence. So if downtimes a matter of your concerns, then Ignite, as it was shown, even with this test, with these benchmarks, and Ignite can read from disk. Ignite native persistence is database. We can read from it. And when it comes to restarts or any downtimes, as soon as your Apache Ignite cluster is reconnected, you don't need to wait a while Ignite preloads all the data from disk to memory. Ignite will read all the data from disk for you. Your applications will be up and running. And then in background, it will be warming up your memory space so that with every second, your queries are running faster and faster and faster because more and more data is loaded in memory. That's what Ignite does.
Okay, so one for Simon. So how does Azul Zing garbage compare compares to ZGC? There were quite a few questions about ZGC. So if you scroll up, so people asking those.
Yeah, so the idea with ZGC is that they've taken a very similar approach to what we've done, and so they use the idea of rebarrier as well, which is obviously something that is a way of solving one of the problems, and they are not as pauseless as us, so they do have pauses in their algorithm. So there are small pauses involved in what they do. The other thing is that with ZGC, it's still experimental. So I'm not aware of anybody who's actually using it in production yet. I believe in JDK 15, it's slated they're going to take the experimental option off that. But I still think that there's quite a way to go in terms of stability before it'll be as solid as Zing. In terms of performance, it's difficult to say because we don't have benchmarks that we actually publish on this. They're going to get similar results to us in some circumstances, and different results to us in other circumstances.
So there was another question. I'm going to paraphrase it rather than reading it out exactly, which is there must be some sort of costs to using Zing. It can't be like you just have absolutely get everything for free. So.
Yeah, so this is a good point, you see, because obviously if you're going to do garbage collection has to go somewhere. So if you take out the pauses that you get in terms of using a typical garbage collection algorithm, then the work has to be done concurrently, which is what the algorithm is, concurrently with the application threads. So effectively what you're doing is reducing the throughput that you would get with your application. So that you could look at and say, oh, that's a bit of a problem. But what we've done is by using Falcon to improve the overall performance of the application code that we generate from the compiler, we can actually eliminate the reduction in throughput by improving the efficiency of the code that we generate. So you get the double hit. You get the fact that you're not getting pauses for the garbage collection and you're still getting the same throughput because we're improving the efficiency of the code.
The last two questions that I captured were from a long time back, so very beginning of the presentation. So instead of copying objects physically, has it been tried as an experiment to maintain a table where the allocation and deallocation is done? So only the links need updating, maybe faster. What are the issues with that approach?
Yeah, you see, you can't really do that because the point is that if you would have to maintain very, very small pages in effect, and you can't really do that. So you have to have pages that you use within the heap. So if you look at algorithms like G1, they use regions. We use the same idea. We have pages in effect in our heap. So if you're trying to maintain the links, you'd still end up with a lot of wasted space where objects were no longer being used in a particular page. So by compacting it it's much more efficient. It's much more better in terms of the overall efficiency of the algorithm. Because if you didn't do that, ultimately if you kept it running for long enough, you get to the point where fragmentation would be too bad, and then you would have to do what everybody else does, which is to stop everything and do a full compacting collection. So it just isn't as efficient doing it that way.
Okay, so the last question that I have copied here is with the new JVM CI implementation and also the implementation to slot in custom GCs, is it possible to hook in the C4 and Zing collectors to OpenJDK 10 and above JDKs stroke JVMs?
Yeah, I mean, we use the compiler interface because that came in far enough back that we could use that in some of the work that we did with Falcon. What we're doing in terms of Zing is we're not following the 6-month release cycle. So we're following the LTS release cycle for Zing, meaning that we have a Zing for JDK 8 and we have a Zing for JDK 11, and the next one will be Zing for JDK 17. Now, yeah, I mean, what we found is that the customers we have for this are looking for stability. So they don't want to update every 6 months. They're quite happy with updating every 3 years. So we don't need to be moving to JDK 10, JDK 13, JDK 14, and so on. So yeah, we have a Zing for JDK 11. So we can do all of the things in JDK 11, and the next one will be JDK 17.
Okay. So there is a conversation that is happening. I don't know whether there are questions or not. So on the chat about fraud detection and all. So any other questions? If somebody has, they can pop it into the chat with a question mark over there. We can wait a minute or so for some more questions. I understand that we are way above time, but we can probably give people a minute or so for last couple of questions. Open source, Simon, Zing, any chances of it becoming open source?
Not at the moment, no, because we are a commercial organization, so we are not anticipating open sourcing it anytime soon.
Okay.
I can also see some questions related to Ignite. And, one of them is from Matt, and he was saying that off-heap was a solution when garbage collector poses were untenable, and then heap was a licensed enterprise. So to some degree, that's right understanding. But I also would say that with our page memory, that's how we name it, our off-heap memory is page memory. We anyway would be using our own, because the way how the data is stored in memory in Ignite is the same the way we store it on disk. So whenever the pages with your records are being moved back and forth between memory and disk, we are using the same format. And that's much more efficient for us. So whenever we are redesigning our memory architecture, keeping in mind that, yes, we need to have a brand new off-heap memory, we need to have our native persistence, we kept this in mind that this kind of translation between memory and disk must go smooth. So I would say that that's why we would use, and I do believe that some of the Apache Ignite users can use, they use kind of large Java heaps, but that was one of the other motivations why we need our own off-heap memory region to be able to work efficiently with our disk tier.
Thanks, Dennis. Mani is asking, maybe older versions of Zing can be open sourced or freeware or something like that?
Well, no, I mean, the thing is that the C4 algorithm is like the magic sauce, if you like. So even the older one, I don't see us open sourcing it anytime soon. Cool. I mean, we have made the algorithm public. I mean, you can read the paper that was written on how it all works.
So there's another one from Mani, which is, how is the off-heap approach going to work with higher versions of JDK, where unsafe and off-heap-like access is going to get restricted?
Yeah, I would say that access was restricted from the very beginning. At least it was never suggested, right, to use those APIs. But right now we don't have any issues, and Ignite memory works with the latest versions of JDK. But anyway, the community folks, they already know what would be a substitution So Oracle finally, yes, they are saying that. So right now, application developers need to pass in special parameters to the JVM to enable those unsafe methods. But at least right now we have some public interfaces that would let us, to replace unsafe with some public API officially. So it's just, a task to do, but we don't. It's not a high priority for us.
Sure. All right, then I think, are you going to come up with alternative ways of off-heap access?
No, that's what I'm saying. There are some public APIs, alternatives that are available right now, at least for our memory architecture.
Okay, cool.
It will not be a rewrite. It will not be a rewrite. It's just, about updating some of the internal implementation interface.
Sure. Right then, well, thank you very much, Simon and Dennis, for such a captivating introduction to Zing and also to Apache Ignite. I'm sure everybody gained a huge amount out of this. So thank you very much.
Thank you.
And Omar, how about raffling the books? Do we have time for this? 3 minutes?
Sorry, what about the books?
The books. We can. I think that we can give them away right now, if the guys want to do that. Otherwise, we can reach out attendees.
The only thing is that we are way out of time. I mean, if people are willing to stay, yes, I can. But I'm sure. I mean, we are probably 70% down from the strength that we started. So I'm sure people must be taking the survey. Do you have any results? Have people taken the survey?
Hi, yes, we have some responses and we can reach out to winners
okay,
by email.
By email, yeah, that would be great. I mean, we can check if they are here. You can shout them out.
Yes, let me just we have a button random winner, and let me check if Garame Auckland. I'm sorry if I pronounce it wrong. If you are here, can you please send us in chat something?
Graham Auckland, I don't see him.
Okay, one moment. Bennett Hagen.
We have Bennett here.
Oh, cool. Bennett, can you please type us which book would you like to have? And our last winner is Daphne.
Do you have Daphne here? Please type in the...
Yeah, Daphne, can you please type us which book would you like to have?
I don't think we have Daphne at the moment.
Okay, we'll contact her by email. Bennett, I will send the ebook to you and we'll contact you to make sure everything was correct.
Awesome.
Thank you.
Thank you very much, everyone. Thank you for joining and thank you for the presentations. Bye.